Okay, let's continue the section 13.1. In the last part, we know there is a general term for a sequence. When you have the general term, for example, Bn is equal to like n squared, you can directly write down the concrete value for the certain specific position. For example, if you have B10, that will be 10 squared is 100. Okay, it's very simple. And there is another way to define the sequence. So how do we define the sequence? You have the value at nth position, the nth term. The nth term is not directly given, for example, like this. Nth term is not directly given n squared. Nth term depends on one or more of the terms preceding it. So the nth term depends on one or more of the terms preceding it. And this is called recursively defined. Recursively defined sequence. Okay. And that formula, the dependence, is called the recursive formula. The formula is called the recursive formula. Okay, so it sounds very abstract. Let's use some special example to clarify it. So, for example, we define the first number, S1 is equal to 1. And after S1, Sn, the nth term, it is n times the preceding term Sn minus 1. Okay, so now let's see for n is greater than or equal to 2. The first one is specially defined, and the rest of them is defined by this so-called recursive formula. The definition only depends on its preceding term, just one term. It may depend on one or more terms. Okay, so let's try it. S1 is 1. Then what is S2? S2, by definition, you have to use this relation. S2 is n is equal to 2, so it's a 2 times, when n is 2, 2 minus 1 is 1, so it's 2 times S1. So S1 is 1, so 2 times S1, 2 times 1 is equal to 2. And S3. S3, you still follow this pattern. Sn is n, so it's 3, S3 minus 1, 2. 3 minus 1, 2. So S3 is 3 times S2. S2 is 2. S2 is also 2 times 1, so it's 3 times 2 times 1. This is S2. S2. Okay, so 3 times 2 times 1 is 6. And if you observe it, you see it, it is 3 factorial. And here, 2 times 1 is 2 factorial. You can continue this evaluation. S4, we already did 2 examples. So S4 is 4, S3, 4 minus 1 and 3. 4 times S3. S3 is 3 times 2 times 1 here. This is S3. 4 times 3 times 2 times 1. This is exactly 4 factorial, 24. 4 times 6. 4 times 6, 24. And from this pattern, you can see that this recursively defined recursively defined sequence is what? Is the factorial sequence. Here Sn is actually equal to n factorial. Sn is equal to n factorial. So that's our example, first example. So whenever you have recursively defined function sequence, you just try to evaluate step by step. You cannot jump. You cannot say now let's evaluate as 100 maybe. If you define as 100, possibly you need as 99. To define as 99, you need as 98, and then you need as 97. So for recursively defined sequence, you must go from 1 to 2, 2 to 3. You must follow the order. To evaluate recursively defined sequence, one needs to follow the order. You need to know S1, S2, Sn, and so on. You cannot jump. You may not be able to jump to Sn directly. You may not be able to jump to Sn directly. You have to go step by step. And after a few examples or computations, you possibly can guess the general term. But before that, there's no way to get the general term directly. Okay? Let's see another one. Another one is the following. You see, we define U1 as 1, U2 also 1. And when n is greater than or equal to 3, start from the third term. Un is un minus 1 plus un minus 2. Okay, so let's try it. This is the recursively defined sequence. We just try to do evaluation. Let's see what is evaluation. U1 is 1, U2 is 1. So U1 is 1, U2 is 1. And let's start U3. When n is greater than or equal to 3, U3 it is n is 3. 3 minus 1 is 2. 3 minus 2 is 1. So U3 is actually U2 plus U1. U2 plus U1. U3 is equal to 2. U4. n is 4. 4 minus 1 is 3. 4 minus 2 is 2. So U4 is U3 plus U2. U3 plus U2 is 4. So what is the pattern? So you first get 1 and 1, and the 3 means the sum of these two numbers. You get 2. So this is U3. U4, what is U4? You get this one plus this one. Sorry, how do I get 4? This is a 3. It's a mess. My problem. So 1 plus 2 is a 3. This is U4. U1, U2, U3, U4. What is U5? U5, you're going to add 2 with a 3. You will get 5. 2 plus 3, you get 5. This is U5. And let's continuous pattern. You get 3 plus 5, get 8. This is U6. And 5 plus 8, you get 13. This is U7. So every time you just add 2 preceding numbers or 2 preceding terms, you get your current term. Okay, so that's the way to determine the corresponding position, the value in the corresponding position. And also you can see that if you don't if you don't go it step by step, for example, I ask you what is a U10. For U10, you need U9, you need U8. In order to get U10, you need U9 and U8. U9 need U8 and U7. Okay, and U8 you don't know, but U8 you know it's a U7 plus U6. So 7 plus 6 is 8 plus 13, 21. So you get U8. From U7, U8, add these two numbers, it's 34. You get U9. And when you have U8 and U9, you add them, it's 55. So if you want to get the value U10, you have to go through this process step by step. And this sequence is very famous and important. This is called a Fibonacci sequence. Fibonacci sequence, and all the numbers are called the Fibonacci numbers. The terms of this sequence are called Fibonacci numbers. Okay, Fibonacci numbers or Fibonacci sequence is recursively defined. Recursively defined. Okay, so that's the general or the quick introduction about the sequences. You just get a sequence of number by the English. When we have some numbers, of course, we can add them. So we have A1, A2, A3, A4, a lot of number, AN, and continue. Let's just first stop at a certain position. Okay, when we have those n terms, we are going to add them because we can. Okay, so that is the sum of the first n terms. Each one is called a term. The first term, second term, third term, fourth term, nth term. You add the first n terms together. It's a sum of first n terms. You see here, it is very long. The writing is very long. We want a short notation for this long writing, just a notation. How do we know it? How do we write it? We use a Greek letter, sigma. It represents we are going to do the sum. We are going to add this sequence. This sequence is denoted by A something. So we write A K. A sub K. K means, you see here, the first term, second term, third term, fourth term. So K starts from first term. So K starts from first term. K stops at nth term. K stops at nth term. So the sum of AK, the sum of the terms from sequence A, the sum of the terms from sequence A or of sequence A, and then from 1 to n. K is from 1 to n. So it means K will be K is 1, K is 2, K3, K is 4, up to K is equal to n. K is not a single number. K will change one by one every time you repeat, every time you add 1. So K is 1. Next time you add 1, you get K equal to 2, and K equals to 3, K equal to n. And this K is called the index. It's just a name, an index. That's the sigma notation or the sum notation. Okay, so let's try. In this sigma notation, you must say case 1, case 2, case 3, case 4, case 5. You cannot miss term or add additional term between them, right? Like this, you have to add all first n terms together. You cannot say, let's add the first one, third one, fourth one, sixth one, fifth one. You cannot miss any term. If you miss any term, you have to write in the detailed form. If you don't miss any term, you just regularly add from first to nth term, you can use this simplified symbol. Okay? So for example, sigma k from 1 to n, 1 over k. So the formula is like 1 over k, and the k is from 1 to n. K is 1, 1 over k is 1 over 1 is 1. And then sigma is always addition. It's always addition. And k is 2. Whenever after you evaluate the k, you are going to do addition. When k is 2, it's a 1 over 2. 1 over 2. K is 2. And you finish that, you add. K, and then next, you see here, k is a 1. This is 1. This is 2. And next one, you will say k is a 3. When k is a 3, 1 over 3 is 1/3, and addition. And da da da, until you let k is equal to n. When k is equal to n, you get a 1 over n. This is the last value for k. After you evaluate k equal to n, you stop. So this is a sum of the first n reciprocal numbers. 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and stuff. So this short symbol just means this long expression. Okay? Okay. B. Sigma k from 1 to n, k factorial. So what does this mean? This means first you let k be 1. You have k equal to 1, so that's 1 factorial. Right? You finish the evaluation of this symbol. Let's not evaluate, just write it, a formula like 1 factorial. And then you do addition, add k equal to 2. K equal to 2, you have 2 factorial. And then you get plus k equal to 3, then you get 3 factorial. Until you reach the last one, n factorial, when k is equal to n. Okay? So that is the compact notation, and this is long notation. This is a long notation. From compact notation, you should be able to write it in a long notation. And if you have a long notation, how do you write it in a compact notation? For example, you have 1 square plus 2 square plus 3 square up to plus 9 square. How do you write this one? So first of all, it's a sigma, and you use index k. You see that's the evaluation when k is 1, evaluation when k is 2, k 3, k is 9. So it looks like you square k. 1 square, 2 square, 3 square, 9 square. You square k. And k starts from 1, the first one, and second, third, fourth, fifth, and it stops at 9. Stops at 9. Okay, so that is the compact writing for this long stuff. And here we only write 9 squares. We already use dot dot. If I put here 100 square, definitely you will use dot dot dot. You will not copy 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square, 8 square, 9 square, 10 square, up to 100 square. You spend your whole exam time on the writing. That is not what we want. Okay, now let's continue this. Okay, So you see here, this is a general term. Usually when you have the general term, when you see the general term, how do you write a sigma notation? The general term, instead of write n, you will put k here. So 1 over 2 to k minus 1. You see, when k is 1, when k is 1, 1 minus 1 is 0, 2 to 0 is 1, so that's why here is 1 over 1 is 1. So it implies k is from 1, k stops at n. So that when you have the general term, to write the sigma symbol is relatively easier. Okay, that's from the long form to the compact form. Okay, once we have this sigma notation, remember sigma notation is just a compact writing of the sum with a lot of terms. So whenever the sum has a property, the sigma notation will also have the corresponding property. Okay, so for example, if you have a sequence an, you add them. And before you add them, you multiply every term by a constant c. What this means? This means you first have a1, k is 1, you have a1, you multiply it by c. You finish it, you move to the next. A k is 2, you will have a2, you multiply it by c. So every term, you multiply it by c. For addition, if all the terms have the common factor, you can factor them out. Factor this common factor. So you factor c, you will get a1 plus a2 plus an. And this is, you see here, by our notation, this is exactly the sigma k from 1 to n ak. So what this means? This means when you have a constant coefficient inside the sigma, you can move it forward like factorization. Okay, when you have a constant, you can move it forward. Second, if you have two sequences, you already term by term add them. You have a1 plus b1, a2 plus b2, a3 plus b3, a4 plus b4. You already added the corresponding term from two sequences. And then you add the sum of the sum. This it means you can add a terms together first and b terms separately second, and then you add those two results. Addition means you can just add each part and then add the total sum. You can do addition, you can also do subtraction. Okay, you have addition, you also have the subtraction. Here, I just use the simplest stuff to demonstrate it. We're not going to write it in the long form. For example, we only have a1 plus b1, a2 plus b2. So that's a sum, corresponding sum. First term plus first term, second term plus second term. And then we add them. This, see, we use parentheses. This represents the left-hand side. You add a1, b1, you add a2, b2. And addition, does not need this parenthesis. So I'm going to add A1, A2 together first, and B1, B2 together second. And this corresponds to the sigma AK and sigma BK. This is a sigma AK, and this is sigma BK, just because of this addition. And for the subtraction is similar. So get A1 minus B1 plus A2 minus B2. Okay, it's a subtraction. This is the left hand side. This is this one. And here's still addition, so we don't write the parentheses. I put A1, A2 together, minus B1, minus B2 together. But minus minus is minus, effect out minus sign is B1 plus B2. And again, this is sigma AK and this sigma BK. So that is the difference case. Okay, so that's a property, the basic property for the sigma. These three properties are from the regular addition property. And there's one more thing. So what is one more thing? You have A1, A2, AJ. You add A1, A2 up to AJ, and you can continue this. The next one will be AJ plus 1. Remember, whenever you have a position, the next position will be the current position plus 1. So AJ, the next one is A sub J plus 1. This J plus 1 represent the position, the order of the term, not AJ plus 1. So be careful about this writing. We write A sub J plus 1. We write AJ plus 1. This means you have the J's term plus 1. This means it is J plus 1's term. They are not equal. Okay, so just be careful about the writing. The position is very important. Okay, let's continue. This AJ plus 2, and finally we reach AN. So what is a property? Here is the sigma AK, K from 1 to N, from 1 to N. Here is a sigma AK, K from 1 to J, from first index to the last index. So the difference of these two sigmas will be the sum. Let's see, what is the sum? AK, K starts from J plus 1 and stops at N. So J plus 1 is always the initial term. This bottom part is always the initial term. This top part is always the position of terminal term. Then this part is equal to the difference of the large sum and the small sum. Okay, so this is called the property 4 for the sigma notation. So this piece is total piece minus a head, the head. Okay, so we can always have such a thing. So for example, if you have sigma K from 9 to like 15, sigma K from 9 to 15, it is sigma K from 1 to 15 minus 1 to 15. You add 8 terms, so you subtract K from 1 to 8 AK. You miss from the terms A1, A2 up to A8. Just be careful, here is a shift of the index. It's not from 1 to 9, it's from 1 to 8. Okay, so that's how the basic property. They are very natural. They are very natural. Okay, so even though we have those basic properties, we still need a few starting formulas to initial the computation. So here is the list of the formulas. The sum of constant numbers. So what does this mean? When k is 1, it's a constant. When k is 1, it's a c. It does not change. It does not depend on the position, the index. And okay, and you add. The next, when k is 2, it is still c. K is 3 is c. Up to k is n, it's c. So how many c do you have? You start from 1, 2, 3, 4, 5, up to n. So there are n copies of c. That's by definition of a product. It's c times n. It's a c times n. So that's the first formula. So we actually prove it. And second one we will prove it later today. Okay. So what's this? K is 1, you evaluate term, you get a 1. Add. Then you move to 2. K is 2, you evaluate k is 2. K is 3, you evaluate 3. K is 4, you get 4. K is 5, you get 5. Up to k is n, you get n. So what's this? This is the sum of the first n integers. The sum of the first n integers. And the formula is that it is equal to n times n plus 1 divided by 2. We will see this proof soon. And third, k squared. K squared, we go through this similar process. It means we are going to square 1, we're going to square 2, square 3, square 4, up to square n. So we square all the integers and start from 1, stop at n. We add them. It is equal to n times n plus 1 times 2n plus 1 and divided by 6. And we continue this, we get, this is a first power, second power, and third power. We get 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, up to n cubed. What's this? The formula is n times n plus 1 divided by 2. The whole quantity is squared. In our class, we don't have time to prove them, but in the calculus, you may have the chance to see the proof. They may not be required, but you possibly will see the proof. We will prove this today, not the other two. Okay. They are the starting point of the evaluation. Let's try to evaluate. Some examples. First, if we have sigma k from 1 to 5, 3k. So first of all, what is this? Let's try to evaluate, and then we use the formula. First, when k is 1, 3 times 1 is 3. And then when k is 2, 3 times 2 is 6. When k is 3, 3 times 3 is 9. K is 4, 3 times 4 is 12. K is 5, 3 times 5 is 15. So there's only 5 numbers, so that's why we can do it. And let's add 3 plus 6 is 9. 9 plus 9 is 18. 18 plus 12 is 30. 30 plus 15 is 45. Okay, so it is equal to 45 because you only have 5 numbers. You can do this. And now let's change it the way. Let's apply the properties. First property we apply is a constant. Whenever you have a constant coefficient, you can move it forward. You can move this 3 forward. You can move 3 forward. Whenever you have constant coefficient will be moved forward. You have sigma k from 1 to 5k. Okay? And then you see sigma k from 1 to nk. This one, by the formula, it's equal to n plus 1 over 2. Here n is a 5. So it is a 5 plus 1 divided by 2. Okay? Okay. 5 plus 1 is 6. 6 times 5, this is 30. The product, it's a 30. 30 times 3, 90. Check here. 3, 5, 6, the product is 90. 90 over 2. 90 over 2 is 45. Right? So sigma k from 1 to 5 is 5 plus 1 over 2. B. K from 1 to 10, k cubed plus 1. And for this one, we are not going to evaluate it this way. Even though there are only 10 numbers, but we have k cubed. For example, you have to compute 8 cubed. You have to compute 9 cubed or 7 cubed. We don't want to compute that. So we will directly apply the formula. And before that, we apply the sum rule. You see here you have a sum, sigma of the sum. Sigma of the sum means you are going to put sigma for each summand. You put sigma for the first term and sigma for the second term. Okay, the first one, check here, k cubed, k from 1 to n, is n plus 1 over 2 quantity squared. So here this is n. So the first term is n plus 1 divided by 2 and quantity squared. That's the first sigma. And second sigma, whenever you have a constant number c, you do sigma, it is equal to this constant number times n. So it's a product, it's a 1 times 10, or 10 times 1. Okay, so let's try to evaluate. 10 plus 1, 11. 11 times 10 is 110. 110 over 2 is 55 squared, plus 10 times 1 is 10. Okay, and 55 squared is 3025, and plus 10 is 3035. This is the answer. Okay. And next, k from 6 to 20, 4k squared. You see the coefficient of 4. It can be moved forward, so you get 4 sigma k from 6 to 20, k squared. But this moment, you cannot directly apply the formula. The reason is that all our formulas, k starts from 1. Now your k starts from 6. So be careful about this initial initial index k. It's from 6. If it's from 6, not from 1, how do we do that? Remember there's the false property. If it's not from 1, you can write it as k from 1 to 20 minus k from 1 to 5. Right? Remember this? You just add. You see, it starts from 6, so it means 1, 2, 3, 4, 5. You give it 5 terms and subtract it. Right? This is a property 4. Be careful about this step. It's very important. It's very important. Okay, now we can apply. And this coefficient, this 4 is a coefficient in it. It is a coefficient of the difference, not just one term. From 1 to 20, k squared is here. N is 20, so it's a 20 plus 1. And 220 plus 1, so it's a 40 plus 1 over 6 minus 5 plus 1, 10 plus 1, 2 5 plus 1 is 10 plus 1. Okay. Now let's try. So it's 4 is 20 times 21 times 41 over 6. Here 5 times 6 times 11 over 6. 6 is cancelled. And 6 has a factor 3. 21 has factor 3. 20 has factor 2. Okay, so after cancellation, we will have 10 times 7, 70, times 41, minus 5 times 11, 55. So you do the computation, you will get the answer equal to what? Equal to 2,848. Okay, so that is I'm sorry, not this one. This is a wrong number. It's a 11,260. It's my bad. Okay, so that's the answer. So in this problem, be careful about this initial index. The initial index. Okay, now let's see how do we prove the sum of the first n integers. The sum of the first integers is a special example of so-called arithmetic sequence. What is arithmetic sequence? You see, the sequence of integers, the difference is a fixed number. So next term minus current term is always constant number. A constant 1. So here, an arithmetic sequence is recursively defined by the current term is a preceding term plus a constant for some fixed number d. For some fixed number d. So every time you just add a fixed d. So d is called the common difference. The common difference. Okay, so Example. You have 4, 6, 8, 10. So for example, you have 4, 6. You see here, every time you just add 2. 4 add to 6, 6 add to 8, 8 add to 10, 10 add to 12, 12 add to 14. So you can predict. So every time you add 2. Common difference D is equal to 2. Okay. If Sn is 3n plus 5, for example, if Sn is 3n plus 5, what is Sn minus 1? Sn minus 1. You see, it's like the evaluation of a function. Whenever you see n, you use n minus 1. So 3, you see here n here, you're going to write n minus 1 instead, because here is n minus 1 plus 5. Okay, so what do we have? We have 3 Sn. Sn is 3n plus 5, and this is 3n minus 3 plus 5. So it's a 3n plus 5 minus 3. 3n plus 5 is Sn minus 5. So Sn minus 1 is equal to blah 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 Sn minus 3. So Sn is Sn minus 1 plus 3. You just move this 3 to the other side. It's plus 3. So the D is equal to 3 is the common difference. Okay, you get a common difference. And whenever is a linear function of n, the sequence is arithmetic. So that's here we finish the example, and this is the general statement. Whenever you have a linear function in terms of n, then you have an arithmetic sequence. Okay. For the arithmetic sequence, we want to add them. And before we add them, you have this recursively defined the sequence. We want to know the general term. What is a general term? With the general term formula, we can add them. General term a1. A1 is one term, and next term a2 is a1 plus d. Every time you just remember that's the meaning of the recursively defined. Every time you just added a constant number. Common difference. A3 is A2 plus D. Remember, it's the preceding term plus D. But A2 is A1 plus D, so it's A1 plus 2D. Right? So it's like this. You start from A. You get a gap. You get A2. This is a gap D. You get another gap. You get A3. But 3 means from A1 you get a 2D. Then you get a next one, A4. A4 means from the first term you get a 3D. This is D, D, you see, 3D. So 4, 3D, 3, 2D. So if you continue this, AN, it will be, you start from the original part, you get N minus 1D. So this is the general term. This is a general term. the general term of the arithmetic sequence is always the first term plus n minus 1 times d. So okay, so that's a theorem. Nth term of an arithmetic sequence. Let A1 be the first term and D be the common difference. Then the general term An is equal to A1 plus n minus 1 times D. Okay, so let's see the example. Find the 41st term of the arithmetic sequence 2, 6, 10, 14, 18, and so on. So that's a question. Find the 41st term of the arithmetic sequence. So from this, you see that A1 is equal to 2. The first term is 2. The common difference, how do we get common difference? You get whatever pair, you do the difference. 6 minus 2 is 4. So the common difference is 4. First term is 2. Then A41 is A1 plus 41 minus 1 times D. So it's n plus 1. So A41, A1 41 minus 1. Okay, so it's 2 plus 40 times 4. 40 times 4 is 160, so 162. 162. So we can quickly determine the general term or general formula for the arithmetic sequence if we know the initial term plus the common difference. So the general term is determined by two quantities, A1 and D. Okay. Now let's see the example. The 8th term is of an arithmetic sequence. Is 75. The 20th term is 39. Okay. First question. Find the first term and the common difference. Find A1 and D. How do we find them? We should start from the formula. 8th term, A8, It is A1 plus 8 minus 1 times D. A1 plus 7D. It is 75. A20. A20 is A1 plus 20 minus 1 times D. 20 minus 1 is 19. 39. So we actually have a system of equations. How do we solve this system equation? We use equation 2 to subtract equation 1. Equation 2 minus equation 1. Why do we do that? Because A1 minus A1 is 0. 19D minus 7D is 12D. 12D. And 39 minus 75 is negative 36. Check it, it's negative 36. So 12D is negative 36, then D is negative 3. So we do this one subtraction, we get D equal to negative 3. You get D equal to negative 3, you go back to the first equation. A1 plus 7 times negative 3 is equal to 75. So A1 minus 21 is 75. So A1 is 75 plus 21 is 96. 96. So D is negative 3, A1 is 96. B gave a recursive formula. Recursive formula is the following. A1 is 96. You have to know where you start, and you have to know the common difference. An is An minus 1 plus D. Plus D. D is negative 3 plus negative 3 is minus 3. So this is a recursive formula. Find the general term. What is the general term? An. An is A1, N minus 1, and D. A1, 96. N minus 1 times D. D negative 3. Okay, so let's continue the computation. So 96, negative 3 times N, negative 3N. Negative 3 times negative 1 plus 3. So 96 plus 3, 99 minus 3n. So the general term is 99 minus 3n. Okay, so that's the example. How do we determine the initial term, this A1 and the common difference? We need at least 2 terms. You have 2 terms, you can have 2 equations. You solve the system equation, you get the general term. Okay, so after so many information, we still don't know the formula of the sum of arithmetic sequence. Arithmetic sequence. Let's try to write a few terms. You see, A1. A2, what is A2? A1 plus D. What is A3? A1 plus 2D. What is A4? A1 plus 3D. Continue. And you're going to add them. Remember, you're going to add them. Up to, what is an? a1 plus n minus 1d. This is an. I put the parentheses to emphasize. This represents one term. And in order to add them, we have a very famous trick. We're going to switch the order, change the order, and write this sequence again. So we will write a1 plus n minus 1d first in the column. And before it, it is a1 plus n minus 2d. Every time you lose some d. The d you see here, d, 2d, 3d, 4d, 5d. And if you go backward, it's like 10d, 9d, 8d, 7d. Every time you lose a d. Here, lose means you subtract. Here's a1 plus n minus 3 times d. And this one is a1 plus n minus 4 of d. Up to the final one is a1. Okay, so what is this? We write it in the ascending order and the descending order. The magic is the following. You see here, this sum, a1, n minus 1d. So the sum is 2a1 plus n minus 1d. The first column. And check this column. a1, 2a1 plus, here's d, here's n minus 2d. You add them, it's still n minus 1d. And then you continue the check of this column. First column, second column, third column. a1, 2d minus 3d. So it's n minus 1d. So we just continue this check. This is the last one we can check. a1, 3 n minus 4. You add them, it's n minus 1d. Until the last one, the same thing. a1, n minus 1d. So if you add them column by column, you have a constant term. How many constant number do you have? You have n constant numbers. Why? First, second, third, fourth, up to n. So you have n numbers. N constant number, you add n constant number together. It is equal to this number times n. Okay, so you add those two rows, it is equal to the sum of n constant numbers. So it's a constant number times n by the product. But you remember you have two rows, you repeat them. So for each row, it's just half of it. So what do we have? We have a1 plus a2 plus a3 plus a4 up to plus an. This is an. It is equal to 2a1 plus n minus 1d, the whole thing times n divided by 2. Because you have two rows, the same thing. You add them, so you get twice. This is 2 times of each of the row. So you divide by 2, you get 1 row. And this is a formula. We actually have another form. How do we get another form? This is 2a1. First of all, this is one formula. You can use it. And another representation for the same formula is the following. 2a1, we write like a1 plus a1 and plus n minus 1d divided by 2. Okay, and a1 plus n minus 1d check what it is. A1 plus n minus 1d is an. This is a second formula. So the second formula tells us if you have an arithmetic sequence, you want to add them. You pick up the initial term, you pick up the terminal term, you add them times n divided by 2. Okay, so initial plus terminal times n. N means how many numbers you have, times n over 2 is a sum. This formula is only applicable for arithmetic sequence. It is only correct for arithmetic sequence. So this is the general formula. Now let's see how do we get the sum of the first n integers. First of all, this is an arithmetic sequence. It is an arithmetic sequence. Then the sum is initial term plus terminal term times n and over 2. So that's exactly the formula we read. Okay? And remember that we mentioned if you have a linear function in terms of n, then that sequence is arithmetic. So for example, if you have an equal to 3n plus 5, this is arithmetic. And its first term, n is 1, 8. The nth term is 3n plus 1. So the sum of the first n terms is what? Sum of the first n terms, sum from 1 to n. The sum of the first n terms, akk from 1 to n. It is equal to the initial term plus an, the terminal term. There are n terms and divided by 2. Initial term plus a terminal term times the number of the terms and divided by 2. There are n terms, so you put n here. And yeah, that's so if you want to write like the 3n plus 13 times n and over 2. When you have n, you will get the corresponding number. But this is abstract, the general number. And we can also verify it with the formula we already know. Let's see. We try to add an, the first n integers. So it's a 3n plus 5. 3k plus 5, k from 1 to n. Remember, sigma can be distributed into the sum. Right? So we have distribution. The coefficient can be moved forward. And the sigma of a constant is a product, 5 times n. And this part, the sum of the first n integers, n plus 1 over 2 plus 5n. Then are they the same? And let's check. So 3 times n plus 1, so 3n squared plus 3n. 5n, this is 10n over 2, so plus 10n total thing over 2. So it's a 3n squared plus 13n over 2. Here, if you write one more step, 3n squared, 13n over 2. See, it's identical formula. So either way, you will have the same stuff. You have the same stuff. Okay, so now let's use arithmetic sequence to add some stuff. Find the sum. 60, 64, 68, 72, up to 120. Up to 120. So you check here. It's add 4, add 4, add 4, add 4, add 4. Finally, it's 120. So this is arithmetic sequence. It's supposed to be arithmetic sequence. And the formula will be 6 initial term plus 120 times the number of the terms divided by 2. The question is, what is this n? How many numbers do we have? How many numbers do we have here? Okay, so we gave them name. So we will call this A1, this A2. This one will be an. This n is this n. Okay, those two are the same. So how do we determine it? An is a1 plus n minus 1 times d. A1 is 60. D, you do the subtraction, you know D is 4. D is 4. Every time you just add 4. Okay, so 120 is 60 plus 4 times n minus 1. So it's a 60 is 4 times n minus 1. You divide by 4, 15 is n minus 1. So you get n is 16. Okay, very good. Once you get n equal to 16, the sum is 60 plus 120 times 16 divided by 2. Do this computation. It is 1,440. 4,040. Okay, so this is the last example for this semester. Okay, so you have to be able to apply the arithmetic sequence to find sum. Like this. Okay, we stop here today, and we stop the whole semester. Do the recommended exercise. Make sure you know how to do them. The final exam will depend on your practice. Thank you very much.